A clock is ticking somewhere above Earth. It is not far, by cosmic standards, only a satellite moving quietly through orbit circling the planet while cities sleep beneath it. But that clock is not keeping time exactly like the clocks below. It is moving fast, so one effect slows it down slightly. It is also farther from Earth's gravity, so another effect makes it tick slightly faster. The difference is tiny, far too small for a human heartbeat to notice yet. Without correcting it, the maps in our pockets would begin to drift. That small betrayal is the doorway into one of the deepest mysteries science has ever found. For most of human history, time felt like the one thing no one could negotiate with. A second was a second. Space was the silent stage around us. Gravity was the familiar pull that kept our feet on the ground and the moon in the sky. We lived inside this world so completely that it seemed almost impossible to imagine another one. The ground was solid. The sky was distant. The present moment felt as if it belonged to everyone at once. Then Einstein began asking questions that sounded almost childlike, but carried the power to unsettle everything. What would happen if you could chase a beam of light? What does a falling person feel? Why should every observer agree on the speed of light, even when they disagree about distance and time? And if gravity can disappear inside a falling elevator, was gravity ever really a force in the way we thought? From those questions came a new vision of reality. Space and time were no longer separate. They became spacetime, an invisible structure, woven through every motion, every orbit, every beam of light, and every falling body. It could stretch. It could curve. It could slow clocks bend, starlight close around black holes, and ripple outward when the darkest objects in the universe collide. Tonight we are not entering space-time as a dry definition or a set of equations. We are entering it as a mystery, one that begins with a clock, passes through light, gravity, the sun, black holes, and gravitational waves, and ends at a question even Einstein did not close. If space and time are not the fixed background of reality, then what are they? And if space-time itself can bend, shake, stretch, and perhaps break, what is the universe truly made of? Imagine standing in a quiet room with two clocks. They are identical, polished, carefully made, and placed side by side on a table. Their hands move together. Their seconds match. Their rhythm feels so ordinary that no one would think to question it. One clock says now, and the other agrees. This agreement is one of the invisible comforts of human life. We move through the world assuming that time is shared. Morning arrives for everyone. A minute is a minute. A birthday passes once. The past is behind us, the future ahead, and the present seems like a single bright edge cutting through the entire universe at once. We may live in different places, speak different languages, and look up at different skies, but deep down we tend to imagine that all of us are carried by the same river of time. That feeling is so natural that it hardly feels like an assumption. It feels like the structure of experience itself. We arrange meetings, measure work, remember childhood count years, and watch the sky turn from morning to evening. Every clock in a city may be imperfect, but the imperfection seems to belong to the clock, not to time. Time itself feels like the quiet authority behind all clocks. For Isaac Newton, this intuition had a grand and powerful form. Time in the Newtonian picture flowed evenly without depending on anything outside itself. Space, too, was imagined as a vast stage, an empty framework in which objects moved. The planets traveled, stones fell, tides rose, and cannonballs curved, but the background itself remained fixed. It was a majestic picture. Newton did not merely give science equations. He gave the universe a kind of deep mechanical dignity. The same laws that governed falling bodies on Earth could describe the moon's orbit and the motions of planets. The heavens and the ground were no longer separate kingdoms. They belonged to one intelligible order. For generations, this order worked with astonishing success. Ships could navigate, astronomers could predict planetary motion, engineers could build machines and bridges. The world seemed to have become legible through force, mass, distance, and time. Space was the place where motion happened. Time was the measure by which motion unfolded. Gravity was the attraction that held the cosmic arrangement together. And for ordinary life, this picture still works beautifully. If you drop a cup, you do not need general relativity to watch it fall. If you build a bridge fire, a simple projectile, follow the path of the moon across the sky, or measure the passing of a workday, Newton's universe remains wonderfully useful. That is one reason the older picture felt so natural. It did not merely satisfy intuition. It worked. But nature sometimes hides its deepest strangeness in places ordinary life never reaches. The cracks begin when speed becomes extreme, or gravity becomes strong, or measurement becomes precise enough to notice what the senses cannot feel. A human body cannot feel the difference between two atomic clocks placed at slightly different heights. A passenger cannot look at a satellite and sense that its clock is drifting differently from one on Earth. Yet these small differences are real. A clock higher above Earth, where gravity is slightly weaker, ticks a little faster than one closer to the ground. A clock moving very quickly ticks a little slower than one at rest relative to the observer. In daily experience, these effects are so tiny that they vanish beneath ordinary perception. But in the careful language of physics, they cannot be ignored. This is where common sense begins to betray us. Common sense was shaped by walking speeds, falling stones, campfires, seasons, heartbeats, and shadows. It was not shaped by light moving at nearly 300,000 kilometers per second. It was not shaped by atomic clocks. It was not shaped by satellites circling Earth or particles racing near light speed in accelerators. So when the universe is measured at those extremes every day, intuition begins to lose authority. Einstein's revolution begins with this loss. Before we reach curved space-time, black holes, or gravitational waves, we have to pause over a quieter shock. Time is not the same for everyone. It does not flow as a single universal river. It depends on motion. It depends on gravity. It depends on the path taken through the universe. That sentence can sound abstract until we return to the clock above Earth. A navigation satellite carries clocks that must be extraordinarily precise. Those clocks are moving quickly in orbit, which tends to make them tick slower relative to clocks on the ground. But they are also farther from Earth's mass, where gravity is weaker, which tends to make them tick faster. Engineers must account for both effect, and if they did not, the positions calculated by GPS would grow wrong. This is one of the most astonishing quiet facts of modern life. Every time a phone locates itself on a map, it is relying in part on Einstein's strange vision of time. The theory that once seemed like a remote philosophical disturbance now helps guide cars through cities, ships across oceans, aircraft through the sky, and people through unfamiliar streets. Space-time is not only out beyond the stars, it is in the correction hidden inside an ordinary device. But the deeper meaning is not technological. The deeper meaning is that time is local. A clock does not simply read the time of the universe. It records its own path through space-time. Two clocks that begin together can separate, move differently, experience gravity differently, and later disagree. The disagreement is not a flaw in the clocks. It is a clue about reality. This is difficult to feel because we do not experience time from the outside. We cannot step beyond time and watch it flow. We cannot compare the whole universe to a master clock hanging somewhere beyond the stars. We only ever experience time from within a path, from within a body, from within a local frame. The clock on your wrist, the clock in a satellite, and the clock near a massive star are not measuring a universal stream in the old sense. They are measuring time along their own journeys. There is a strange intimacy in this idea. It means that time is not only something measured by observatories, laboratories, satellites, or equations. It is also something written quietly into every body. Your feet, closer to Earth's center, are in a slightly stronger gravitational field than your head. The difference is far too small to matter in any ordinary human feeling, but the principle is real. Even standing still, you are not occupying one perfectly uniform time from head to toe. This is not how time feels. A person standing in a room feels whole. A body does not feel divided into layers of slightly different gravitational time. The mind does not notice the tiny difference between the floor and the ceiling. Yet physics says the difference is there, not as a poetic suggestion, but as a measurable truth when instruments become precise enough. That is one of the quiet shocks of relativity. It does not always announce itself through spectacular cosmic events. It does not require a black hole or a galaxy or a star collapsing in darkness. Sometimes it appears as a whisper inside measurement, a slight disagreement between clocks placed at different heights, a correction inside a satellite system, a tiny drift that only becomes meaningful when civilization builds machines delicate enough to notice. The world of ordinary perception is not wrong, it is simply coarse. It gives us a version of reality smoothed by the limits of the human body. Our senses are extraordinary for survival, but they were never designed to reveal the fine structure of time. We can sense day and night. We can feel age, hunger, waiting, and fatigue. But we cannot feel nanoseconds bending under gravity. We cannot feel simultaneity changing with motion. We cannot feel the geometry beneath the clock. And yet that hidden geometry is present everywhere. A person waiting at a train station, a satellite crossing the sky, a mountain summit under cold stars, a clock in a basement, a spacecraft passing Earth. All of them live inside slightly different conditions of time. The differences may be tiny, but they are not imaginary. They are the small exposed edges of a deeper structure. This changes the emotional texture of time. Instead of a single universal river, we begin to imagine countless streams, each attached to a path, each shaped by speed and gravity, each agreeing with nearby companions until conditions become extreme enough for disagreement to show. Time becomes less like a cosmic ocean and more like a local rhythm carried by every object through the universe. That local rhythm is what a clock records. A clock is not merely a machine counting an external flow. It is a traveler. Its ticking is the history of its own motion, its own height in a gravitational field, its own relationship to the world around it. When two clocks disagree after taking different paths, the disagreement is not a failure of timekeeping. It is the record of two different journeys through spacetime. The human mind resists this because it wants one time, one now, one shared present, one cosmic moment in which every star, planet, person, and particle can be placed. But relativity gently removes that comfort. It does not replace order with confusion. It replaces a simple order with a deeper one. And that deeper order begins with light. In Einstein's world, every observer carries a kind of private slice of time. This does not mean reality becomes random or subjective in a casual sense. Physics does not collapse into personal feeling. The differences obey precise rules. The strange part is that the rules no longer protect the old idea of one absolute time shared by everyone. Instead, they tell us how different observers relate their measurements to one another. The shock lies in how calm the universe remains while doing this. Nothing feels broken. Clocks still tick. Planets still move. A child still grows older. A shadow still lengthens in the afternoon. But beneath the smooth surface of ordinary time, another structure is quietly at work. The familiar world is not false. It is a slow, weak gravity, everyday approximation of a much stranger one. This is often how deep scientific revolutions arrive. They do not always make the old world disappear. They reveal that the old world was a special case. Newton's time works beautifully when speeds are small compared with light, and gravity is not extreme. But when the measurements become finer, or the conditions more severe, the deeper rules begin to show through. That deeper rule changed the meaning of simultaneity. Two lightning strikes that seem to happen at the same time for one observer may not be simultaneous for another observer moving differently. This is not because one observer is confused. It is because at the same time depends on how information travels, and information cannot outrun light. Here the clock leads us toward light. To decide whether two events happen at the same time, we need signals. We need light to carry information from the events to an observer. But if the speed of light is the same for all observers, no matter how they move, then the old picture of time cannot survive unchanged. Something else must give. And what gives is time itself. A moving clock ticks differently. Lengths along the direction of motion can be measured differently. The order and spacing of events become tied to the observer's motion. Space and time are no longer independent containers, one holding positions and the other marking duration. They begin to behave like parts of a deeper structure. At this stage, space-time has not fully appeared, but its shadow is already present. The clock has betrayed common sense, but it has not betrayed reality. It has betrayed only the older human expectation that time must be simple because it feels simple. In truth, the universe was never required to match the scale at which our senses evolved. A second still matters. A day still matters. A lifetime still matters. But beneath those familiar measures lies something stranger. Time can stretch, shrink, and differ between paths. This is why Einstein's mystery is so powerful. It does not begin by showing us something far away. It begins by disturbing something intimate. We all know what it means to wait. We know what it means to remember yesterday, to anticipate tomorrow, to hear a clock in a quiet room. Time seems woven into consciousness itself. And yet physics says, be careful. The time you feel is real for you, but it is not the master time of the cosmos. Somewhere above Earth, a satellite clock is tracing a slightly different rhythm. Somewhere near a neutron star time would bend more severely. Somewhere near the edge of a black hole, the difference would become almost unbearable to imagine. To a distant observer, a clock falling towards such an edge would seem to slow and redden its signals, stretched as if time itself were being drawn thinner. To the falling clock, however, its own seconds would continue locally as usual until the path carried it into a region no outside message could escape. The disagreement is not a mistake. It is the geometry of reality revealing itself through time. This is what makes the subject so difficult and so beautiful. Time is not replaced by chaos. It is not discarded. It becomes more precise, but also more relational. It belongs to paths, observers, signals, and gravity. It is not a single river flowing through all places with one unquestioned speed. The first doorway into spacetime is not a telescope. It is a clock that refuses to be universal. Once that door opens, the next question becomes unavoidable. If time can change, what forced it to change? What principle was so powerful that even the old river of time had to bend around it? Einstein found that principle in light. Not light as poetry, not light as metaphor, but light as a physical speed that would not behave like anything else. To understand why time lost its throne, we have to follow Einstein into one of his most famous questions. What would the universe look like if you could chase a beam of light? Section 2. Chasing a beam of light. Before Einstein became a symbol, before the wild hair and the famous photographs, before the word genius attached itself to him so tightly that it almost obscured the person, there was a young mind troubled by light. He imagined chasing a beam of light. The image is simple enough for a child, yet strange enough to unsettle a century of physics. Suppose you could run beside a light wave. Suppose you could move faster and faster until you nearly kept pace with it. What would you see? Would the wave hang frozen beside you, a motionless ripple in space? This question sounds playful, but it led into a deep contradiction. Maxwell's theory of electromagnetism had shown that light is an electromagnetic wave traveling at a fixed speed. But in ordinary life, speeds add and subtract. If a train moves forward and someone walks inside it, their speed relative to the ground depends on both motions. If you chase a thrown ball, it approaches you more slowly. If you run toward it, it comes faster. So why should light be different? The deeper Einstein looked, the less light behaved like the objects of ordinary life. A stone can be chased. A carriage can be overtaken. A sound wave changes its apparent pitch when source and listener move. But light seemed to occupy a stranger role. It did not merely move through the universe. It helped define how the universe's measurements fit together. If light behaved like ordinary objects, then chasing it should change the speed at which you measure it. But Einstein took seriously a remarkable idea. The laws of physics should be the same for observers moving uniformly relative to one another, and the speed of light in vacuum should be measured the same by all such observers. This is where intuition begins to fail again. Imagine two observers moving differently. One is standing on a platform, another is passing by in a train. A beam of light moves through their shared world. Common sense says they should disagree about the speed of that light, just as they would disagree about the speed of a thrown stone. But special relativity says they do not. They may disagree about distances. They may disagree about durations. They may disagree about simultaneity, but they agree on the speed of light. The universe protects light's speed by making space and time flexible. To feel how strange this is, imagine running after a beam of light across an endless, dark plain. No matter how fast you run, the beam does not slow in the way an ordinary object would. You do not gain on it as you would gain on a cyclist, a horse, a train, or a thrown stone. The speed of light does not become smaller simply because you chase it. Instead, the universe changes the bookkeeping of distance and time so that the light remains light. This is not only a surprising fact, it is a rearrangement of reality's grammar. In ordinary life, speed is a relation between distance and time. If distance and time are fixed in the old sense, then speed should change depending on the observer. But if light's speed must remain fixed, then distance and time cannot remain absolute. The thing we thought was most stable must become flexible to preserve something deeper. Einstein's genius was not just in accepting a strange result, it was in allowing the strangeness to reach all the way down. Many thinkers might have tried to save common sense. They might have searched for a hidden medium, a privileged frame, some invisible cosmic rest state that would allow one observer to be truly right and the others merely distorted. Einstein took another path. He removed the need for a preferred observer. He let the laws of physics belong equally to all inertial frames. That equality is easy to overlook. Special relativity is often remembered for its weird effects, slowing clocks and shrinking lengths. But behind those effects is a kind of democratic structure of physical law. No uniformly moving observer has the final absolute view of space and time. There is no hidden cosmic balcony from which the universe can be seen as it really is in the old Newtonian sense. Instead, each observer measures from within motion. This is why relativity can feel both disorienting and strangely fair. It does not say that truth disappears. It says that truth must be expressed in a way that respects how observers are related. A measurement alone is not enough. We must also know the frame from which it was made. Two observers may disagree about the length of a moving object, the duration between events, or whether two distant flashes were simultaneous. But they can still translate their measurements according to precise rules. Their disagreement is not personal. It is geometric. This is where the mystery starts to deepen beyond clocks. If observers can disagree about time and distance, then reality is not located entirely in either observer's private measurement. Something more stable must lie beneath the disagreement. Special relativity hints that this deeper thing is space-time itself, a structure in which space and time are not separately absolute, but together form a more durable order. This is why the light beam matters so much. A childlike question becomes a doorway into a universe where the old categories cannot survive. Chasing light does not reveal a frozen wave. It reveals that no one can stand beside light as if light were an ordinary traveling object. The attempt to imagine doing so breaks the old world, and through that break space-time begins to appear. This is the heart of the mystery. Light does not negotiate with the observer. Instead, measurements of space and time rearrange themselves so that light remains constant. If one person's clock must slow relative to another, it does. If one person's measurement of distance must shrink along the direction of motion, it does. The old background gives way to a deeper rule. At first, this can feel almost impossible. How can time slow? How can length change? How can two observers both be right when they disagree? The difficulty comes from expecting reality to preserve the categories of ordinary experience. But Einstein was not asking reality to preserve them. He was asking what must be true if the speed of light is invariant and the laws of physics remain consistent. In a quiet way, this is one of the boldest moves in the history of thought. Einstein did not simply add a new force or discover a new planet. He rearranged the meaning of measurement. Space and time were no longer absolute quantities waiting to be read off by any observer. They became relations between events, observers' clocks, rulers, and signals. The word event becomes important here. An event is something that happens at a place and a time. A flash of lightning, a heartbeat, a star exploding, a clock ticking. In Newton's picture, one could imagine all events laid out against a single universal time. Everyone might disagree about where things are depending on coordinates, but the deep time order was shared. Special relativity makes the map stranger. Observers moving relative to each other can slice the set of events differently. What one observer calls simultaneous, another may not. This does not destroy causality, because events that can influence one another remain constrained by the speed of light. But it destroys the idea of a universal now stretching across the cosmos. There may be no single present moment shared by the entire universe. That statement carries a quiet philosophical weight. It means the present, which feels so immediate from within consciousness, is not a cosmic sheet passing through all space at once. It is local, relational, tied to an observer's state of motion. The universe does not come with a preferred clock telling everyone what now means everywhere. Imagine a flash at the front of a moving train and another at the back. Someone standing exactly midway on the train may receive the light from both flashes at the same time. Someone standing on the platform watching the train move may judge the order differently because the midpoint on the train is moving toward one flash and away from the other. Neither observer needs to be careless. The disagreement is built into how light travels and how motion changes the relation between events. This kind of example is easy to draw and hard to absorb. It tells us that time is not merely a container in which disagreements happen. Time itself is part of what can be disagreed about, so long as the disagreement follows precise, relativistic rules. A clock is no longer a window into an absolute cosmic present. It is an instrument following a path. Einstein reached this not through mysticism, but through light signals. To synchronize two clocks at different places, you need to send signals between them. But if signals travel at a finite speed, and if that speed is the same for all observers, then synchronization itself becomes part of physics. Time is no longer something simply given. It must be operationally defined. That sounds technical, but the emotional effect is profound. The world becomes less like a stage and more like a web of relations. Nothing is measured in isolation. A ruler, a clock, a beam of light, and an observer form a system of meaning together. Space and time do not vanish, but they lose their old independence. This is why the thought experiment of chasing light matters so much. If a person could somehow see a frozen light wave, then Maxwell's equations would appear different in that person's frame. The laws of electromagnetism would lose their elegant consistency. Einstein refused that outcome. He chose instead a stranger universe, one where no observer can catch light, because the structure of space and time prevents it. No matter how fast you move, light still flees at light speed. The closer an object with mass approaches that speed, the more extreme the effects become. Its time, as measured by another observer, slows. Its energy increases. The speed of light becomes not merely a fast speed, but a boundary in the structure of reality. It is less like the speed of a thing and more like the speed limit of causality itself. Everything that carries information, influence, or cause through the universe must obey it. This gives light a role that is almost architectural. It shapes what can affect what. It defines the cones of possible influence that later space-time diagrams would make visible. It separates events that can be causally connected from those that cannot. It is the thread along which the universe allows messages to travel. A distant star may explode tonight, but if it is 1,000 light years away, Earth will not know for 1,000 years. Not because our instruments are poor, but because information itself needs time to cross space. The universe is not only large in distance, it is large in delay. Every look into deep space is also a look into the past. This familiar idea becomes deeper in relativity. Light does not simply show us distant objects. It structures what can be known when it can be known, and how cause can move. The night sky is not a single present moment displayed above us. It is a layered archive of signals arriving from different ages. In this sense, Einstein's light beam was not just a physical curiosity. It was a doorway into a universe where seeing, measuring, and existing are tied to finite speed. The world does not update everywhere at once. Events communicate through space-time, and light marks the fastest possible thread of that communication. But special relativity also leaves something unresolved. It works beautifully for observers, moving uniformly without acceleration and in the absence of gravity. It shows that space and time are not absolute, yet it does not fully explain what gravity is. It does not tell us how massive bodies curve paths or why falling feels the way it does. Newton's gravity still waits nearby, powerful and useful, but no longer comfortably aligned with the new vision. There is an unease here. Newtonian gravity seemed to act instantly across space. The sun pulls Earth. Earth pulls the moon. But if nothing can travel faster than light, how can gravity be an instantaneous influence? If the sun somehow vanished, would Earth know immediately or only after light had time to cross the distance? Einstein's new universe could not tolerate action that ignored the speed of light. The problem of gravity now looked deeper than before. It was no longer only a question of why things fall. It was a question of how gravity fits inside a universe where space and time are woven together by light's speed. Special relativity had shattered the old clock, but it had not yet given gravity a home. For that, space and time themselves needed to be reimagined in a more complete way. Einstein had shown that they transform together, but another mind would give that transformation a powerful geometric form. Hermann Minkowski. Einstein's former mathematics teacher saw that relativity was not merely a strange set of effects. It was the sign of a unified world. Space by itself and time by itself, he suggested, were fading into shadows. Only a union of the two would preserve an independent reality. This was the moment when the invisible fabric began to take shape. The story now moves from chasing a beam of light to seeing every object, every observer, every flash, every life, not simply as moving through space over time, but as tracing a path through spacetime. Before Einstein became a symbol, before the wild hair and the famous photographs, before the word genius attached itself to him so tightly that it almost obscured the person, there was a young mind troubled by light. He imagined chasing a beam of light. The image is simple enough for a child, yet strange enough to unsettle a century of physics. Suppose you could run beside a light wave. Suppose you could move faster and faster until you nearly kept pace with it. What would you see? Would the wave hang frozen beside you, a motionless ripple in space? This question sounds playful, but it led into a deep contradiction. Maxwell's theory of electromagnetism had shown that light is an electromagnetic wave traveling at a fixed speed. But in ordinary life, speeds add and subtract. If a train moves forward and someone walks inside it, their speed relative to the ground depends on both motions. If you chase a thrown ball, it approaches you more slowly. If you run toward it, it comes faster. So why should light be different? The deeper Einstein looked, the less light behaved like the objects of ordinary life. A stone can be chased. A carriage can be overtaken. A sound wave changes its apparent pitch when source and listener move. But light seemed to occupy a stranger role. It did not merely move through the universe. It helped define how the universe's measurements fit together. If light behaved like ordinary objects, then chasing it should change the speed at which you measure it. But Einstein took seriously a remarkable idea. The laws of physics should be the same for observers moving uniformly relative to one another, and the speed of light in vacuum should be measured the same by all such observers. This is where intuition begins to fail again. Imagine two observers moving differently. One is standing on a platform, another is passing by in a train. A beam of light moves through their shared world. Common sense says they should disagree about the speed of that light, just as they would disagree about the speed of a thrown stone. But special relativity says they do not. They may disagree about distances. They may disagree about durations. They may disagree about simultaneity, but they agree on the speed of light. The universe protects light's speed by making space and time flexible. To feel how strange this is, imagine running after a beam of light across an endless dark plane. No matter how fast you run, the beam does not slow in the way an ordinary object would. You do not gain on it as you would gain on a cyclist, a horse, a train, or a thrown stone. The speed of light does not become smaller simply because you chase it. Instead, the universe changes the bookkeeping of distance and time so that the light remains light. This is not only a surprising fact, It is a rearrangement of reality's grammar. In ordinary life, speed is a relation between distance and time. If distance and time are fixed in the old sense, then speed should change depending on the observer. But if light's speed must remain fixed, then distance and time cannot remain absolute. The thing we thought was most stable must become flexible to preserve something deeper. Einstein's genius was not just in accepting a strange result, it was in allowing the strangeness to reach all the way down. Many thinkers might have tried to save common sense. They might have searched for a hidden medium, a privileged frame, some invisible cosmic rest state that would allow one observer to be truly right and the others merely distorted. Einstein took another path. He removed the need for a preferred observer. He let the laws of physics belong equally to all inertial frames. That equality is easy to overlook. Special relativity is often remembered for its weird effects, slowing clocks and shrinking lengths. But behind those effects is a kind of democratic structure of physical law. No uniformly moving observer has the final absolute view of space and time. There is no hidden cosmic balcony from which the universe can be seen as it really is in the old Newtonian sense. Instead, each observer measures from within motion. This is why relativity can feel both disorienting and strangely fair. It does not say that truth disappears. It says that truth must be expressed in a way that respects how observers are related. A measurement alone is not enough. We must also know the frame from which it was made. Two observers may disagree about the length of a moving object, the duration between events, or whether two distant flashes were simultaneous. But they can still translate their measurements according to precise rules. Their disagreement is not personal. It is geometric. This is where the mystery starts to deepen beyond clocks. If observers can disagree about time and distance, then reality is not located entirely in either observer's private measurement. Something more stable must lie beneath the disagreement. Special relativity hints that this deeper thing is space-time itself, a structure in which space and time are not separately absolute, but together form a more durable order. This is why the light beam matters so much. A childlike question becomes a doorway into a universe where the old categories cannot survive. Chasing light does not reveal a frozen wave. It reveals that no one can stand beside light, as if light were an ordinary traveling object. The attempt to imagine doing so breaks the old world, and through that break space-time begins to appear. This is the heart of the mystery. Light does not negotiate with the observer. Instead, measurements of space and time rearrange themselves so that light remains constant. If one person's clock must slow relative to another, it does. If one person's measurement of distance must shrink along the direction of motion, it does. The old background gives way to a deeper rule. At first, this can feel almost impossible. How can time slow? How can length change? How can two observers both be right when they disagree? The difficulty comes from expecting reality to preserve the categories of ordinary experience. But Einstein was not asking reality to preserve them. He was asking what must be true if the speed of light is invariant and the laws of physics remain consistent. In a quiet way, this is one of the boldest moves in the history of thought. Einstein did not simply add a new force or discover a new planet. He rearranged the meaning of measurement. Space and time were no longer absolute quantities waiting to be read off by any observer. They became relations between events, observers' clocks, rulers, and signals. The word event becomes important here. An event is something that happens at a place and a time. A flash of lightning, a heartbeat, a star exploding, a clock ticking. In Newton's picture, one could imagine all events laid out against a single universal time. Everyone might disagree about where things are depending on coordinates, but the deep time order was shared. Special relativity makes the map stranger. Observers moving relative to each other can slice the set of events differently. What one observer calls simultaneous, another may not. This does not destroy causality, because events that can influence one another remain constrained by the speed of light. But it destroys the idea of a universal, now stretching across the cosmos. There may be no single present moment shared by the entire universe. That statement carries a quiet philosophical weight. It means the present, which feels so immediate from within consciousness, is not a cosmic sheet passing through all space at once. It is local relational, tied to an observer's state of motion. The universe does not come with a preferred clock telling everyone what now means everywhere. Imagine a flash at the front of a moving train and another at the back. Someone standing exactly midway on the train may receive the light from both flashes at the same time. Someone standing on the platform watching the train move may judge the order differently because the midpoint on the train is moving toward one flash and away from the other. Neither observer needs to be careless. The disagreement is built into how light travels and how motion changes the relation between events. This kind of example is easy to draw and hard to absorb. It tells us that time is not merely a container in which disagreements happen. Time itself is part of what can be disagreed about, so long as the disagreement follows precise, relativistic rules. A clock is no longer a window into an absolute cosmic present. It is an instrument following a path. Einstein reached this not through mysticism, but through light signals. To synchronize two clocks at different places, you need to send signals between them. But if signals travel at a finite speed, and if that speed is the same for all observers, then synchronization itself becomes part of physics. Time is no longer something simply given. It must be operationally defined. That sounds technical, but the emotional effect is profound. The world becomes less like a stage and more like a web of relations. Nothing is measured in isolation. A ruler, a clock, a beam of light, and an observer form a system of meaning together. Space and time do not vanish, but they lose their old independence. This is why the thought experiment of chasing light matters so much. If a person could somehow see a frozen light wave, then Maxwell's equations would appear different in that person's frame. The laws of electromagnetism would lose their elegant consistency. Einstein refused that outcome. He chose instead a stranger universe, one where no observer can catch light, because the structure of space and time prevents it. No matter how fast you move, light still flees at light speed. The closer an object with mass approaches that speed, the more extreme the effects become. Its time, as measured by another observer, slows. Its energy increases. The speed of light becomes not merely a fast speed, but a boundary in the structure of reality. It is less like the speed of a thing, and more like the speed limit of causality itself. Everything that carries information, influence, or cause through the universe must obey it. This gives light a role that is almost architectural. It shapes what can affect what. It defines the cones of possible influence that later space-time diagrams would make visible. It separates events that can be causally connected from those that cannot. It is the thread along which the universe allows messages to travel. A distant star may explode tonight, but if it is 1,000 light years away, Earth will not know for 1,000 years. Not because our instruments are poor, but because information itself needs time to cross space. The universe is not only large in distance, it is large in delay. Every look into deep space is also a look into the past. This familiar idea becomes deeper in relativity. Light does not simply show us distant objects. It structures what can be known when it can be known, and how cause can move. The night sky is not a single present moment displayed above us. It is a layered archive of signals arriving from different ages. In this sense, Einstein's light beam was not just a physical curiosity. It was a doorway into a universe where seeing, measuring, and existing are tied to finite speed. The world does not update everywhere at once. Events communicate through space-time, and light marks the fastest possible thread of that communication. But special relativity also leaves something unresolved. It works beautifully for observers moving uniformly without acceleration and in the absence of gravity. It shows that space and time are not absolute, yet it does not fully explain what gravity is. It does not tell us how massive bodies curve paths or why falling feels the way it does. Newton's gravity still waits nearby, powerful and useful, but no longer comfortably aligned with the new vision. There is an unease here. Newtonian gravity seemed to act instantly across space. The sun pulls Earth. Earth pulls the moon. But if nothing can travel faster than light, how can gravity be an instantaneous influence? If the sun somehow vanished, would Earth know immediately or only after light had time to cross the distance? Einstein's new universe could not tolerate action that ignored the speed of light. The problem of gravity now looked deeper than before. It was no longer only a question of why things fall. It was a question of how gravity fits inside a universe where space and time are woven together by light's speed. Special relativity had shattered the old clock, but it had not yet given gravity a home. For that, space and time themselves needed to be reimagined in a more complete way. Einstein had shown that they transform together, but another mind would give that transformation a powerful geometric form. Hermann Minkowski. Einstein's former mathematics teacher saw that relativity was not merely a strange set of effects. It was the sign of a unified world. Space by itself and time by itself, he suggested, were fading into shadows. Only a union of the two would preserve an independent reality. This was the moment when the invisible fabric began to take shape. The story now moves from chasing a beam of light to seeing every object, every observer, every flash, every life, not simply as moving through space over time, but as tracing a path through space-time. At first, Einstein's special relativity could be understood as a strange rulebook for clocks and rulers. Moving clocks slow, moving lengths contract. Simultaneity changes with motion. Light keeps the same speed. These ideas were already revolutionary, but they could still be imagined as separate disturbances to space and time, as if space were one thing, time another, and relativity merely forced them to adjust. Then Hermann Minkowski gave the revolution a new shape. In 1908, he argued that space and time should no longer be treated as independent stages of reality. The separation between them had become unstable. In the new physics, they belonged together. What seemed like space to one observer and time to another could mix depending on motion. The deeper structure was not three-dimensional space plus a separate flowing time. It was a four-dimensional space-time. This is one of those ideas that can be stated quickly and understood slowly. We are used to three spatial dimensions, left and right, forward, and back, up and down. To locate an event fully, however, we also need when it happens. A meeting is not defined by its address alone. A star's explosion is not only somewhere in the sky. A heartbeat is not only inside a body. Every event has both a where and a when. Minkowski's insight was that these should be viewed as parts of one geometric reality, not because time is just another direction exactly like space. It is not. Time has its own signature, its own relation to causality and experience. But in relativity, space and time are interwoven so deeply that separating them depends on the observer. What remains more stable is the space-time interval, a combined measure that different observers can agree upon even when they disagree about distances and durations separately. This shift gives relativity a quiet elegance. Instead of thinking that each observer has a distorted version of space and time, we can imagine that each observer is slicing the same four-dimensional structure differently. The disagreements are real, but they are not chaos. They are different perspectives on a deeper order. Space-time becomes the stage and the script at once. Every object traces a path through it. A person sitting in a room is not motionless in this deeper sense. They are moving through time. Their life draws a world line, a continuous path from birth through every breath and step toward the future. A planet draws a world line as it orbits a star. A photon draws a path through space-time at light speed. A galaxy, a grain of dust, a pulse of radio waves, all have histories written as lines in this invisible geometry. This is a beautiful way to think, but it is also unsettling. If a life is a world line, then the present moment is not the whole of reality. Past and future events can be treated as parts of a space-time structure, though how to interpret that philosophically remains debated. Physics gives a map deeper than ordinary experience, but it does not make the emotional mystery of time disappear. We still live moment by moment. We still remember backward and anticipate forward. We still feel time as flow. Space-time does not erase that feeling. It places it inside a larger structure. For a sleep documentary, this is one of the calmest but strangest images in all of science. Every star and sleeping city, every river and migrating bird, every person listening in the dark, each tracing a quiet line through space-time. The universe is not a collection of objects sitting in space while time moves over them. It is a woven history of events. A mountain is not only a shape in space, it is also a long history through time, rising, eroding, shifting, cooling, cracking. A planet is not only a sphere at a location, it is an entire world line through billions of years of orbit rotation and change. Even a single human breath is an event in space-time, tied to a body, a room, a planet, a star, and the long history that made oxygen possible. This is where physics becomes almost contemplative. The objects around us are not separate from time. They are extended through it. A tree is not only the trunk and branches you see now. It is seed growth, winter rain, sunlight, decay, and future wood, all part of its path. A person is not only a body in a chair. They are memory, motion, heartbeat, aging, and expectation, a living world line moving forward through a local time. Of course, physics does not ask us to experience life this way all the time. Ordinary life needs the simpler view. We say the cup is on the table. We do not say the cup is a four-dimensional history intersecting our present slice of space-time. But the deeper view remains beneath the ordinary one, waiting whenever measurement becomes sharp enough or thought becomes patient enough. Minkowski's space-time also helps explain why different observers can disagree without destroying reality. If two people slice a loaf of bread at different angles, the slices differ, but the loaf is the same. This image is imperfect, yet useful. Observers moving differently can slice space-time into space and time differently. What one observer calls distance and duration, another observer may divide in another way. but the underlying space-time structure holds them together. This is why relativity is not a theory of everything being arbitrary. It is almost the opposite. It reveals a deeper invariant beneath changing appearances. The old absolutes of space and time fall away, but they are replaced by something more subtle, space-time relations, that all observers can translate between. The universe becomes less rigid, but not less lawful. There is another way to feel the shift. Think of a map. A city map shows streets, rivers, bridges, buildings, and distances. It helps you move through space. But the map does not show when things happen. It does not show the morning crowd arriving at a station, the evening lights turning on the slow construction of a tower, or the years in which a neighborhood changes. A space-time map would be different. It would not show only where things are. It would show events. It would show the opening of a door, the departure of a train, the flash of a camera, the birth of a star, the crossing of a signal, the meeting of two worldlings. The universe would not appear as a frozen arrangement, but as a vast structure of happenings. This is why space-time is not merely a clever mathematical packaging. It changes what kind of thing the universe seems to be. In the older image, space is like a room, and time is like a clock on the wall. In the space-time image, the room and clock have fused into a single order of events. There is no room without history, and no history without location. Everything becomes placed in 4 dimensions. A photograph seems to capture a moment, but in space-time, it is only a thin slice through deeper histories. The person in the photograph has a world line extending before and after the image. The light that made the photograph traveled from the sun, or a lamp reflected from a face, entered a lens, changed a sensor or film, and became part of another chain of events. Even a still image is filled with motion when seen deeply enough. This can make space-time feel almost too complete. Where is change? If the whole world line can be imagined as part of a 4-dimensional structure, where is the flow of time? If past and future can be placed within the same geometry, physics can describe relations between events, but it does not dissolve the human feeling of becoming. We still live through time, not above it. We still wait for news, remember. Loss anticipate dawn, and experience the future as unopened. This tension should remain. A documentary about space-time should not pretend that physics has made human time emotionally simple. It has not. Relativity gives a more precise structure, but experience remains lived from within. The listener should feel both sides at once, the serenity of a universe written in worldlings and the mystery of consciousness moving along one of them. That is part of what makes space-time so haunting. It is the structure within which all stories unfold, yet no living being experiences the whole structure directly. We inhabit our own line, our own local present, our own sequence of moments. We can calculate beyond it. We can draw diagrams. We can infer how other observers measure, but we cannot step outside space-time to hold it in our hands. The fabric is everywhere, but never outside us. This is why the next step must involve gravity. A flat space-time can already change our view of time and space, but the universe we inhabit is not empty and flat. It contains matter, radiation stars, galaxies, and dark compact objects. If space-time is the hidden order of events, then mass and energy cannot simply sit inside it like furniture in a room. They must affect the room itself. Still, Minkowski's space-time was flat. Special relativity describes a space-time without gravity, or at least without the full curvature produced by mass and energy. It is a profound structure, but not yet the structure of the real universe in all its weight. Stars exist, planets exist, bodies fall, Light bends. Clocks near Earth tick differently from clocks in orbit. Something more must be added. The next step is gravity. Einstein had already transformed time and space, but gravity remained the great unfinished problem. Newton's law described it with extraordinary success, yet it seemed incompatible with the new rules of light and causality. If space and time were now unified, gravity could not simply remain an invisible force acting instantly across an absolute background. The background itself had begun to move into the story. To understand why this matters, imagine space-time as a map of possible paths. In flat space-time, free objects move along the straightest possible paths called geodesics. A body not being pushed follows its natural route. But in the real universe, planets orbit light curves near massive stars, and falling bodies accelerate toward Earth. If gravity is not simply a force in the old sense, perhaps these paths are not being bent by a pull. Perhaps the geometry through which they move is not flat. This was the astonishing direction Einstein began to take. Instead of asking how gravity acts across space, he began asking whether gravity is a feature of space-time itself. If space and time form one structure, maybe mass and energy change that structure. Maybe a falling object is not being pulled away from a straight path. Maybe it is following the straightest possible path in a curved geometry. This is a difficult idea because human senses are built for surfaces and spaces, not four-dimensional curvature. A curved two-dimensional surface is easy to imagine. An ant walking on a sphere may think it is going straight, even while its path bends in three-dimensional space. But space-time curvature is not simply a bend into some higher visible room. It is a change in the relationships between events, distances, durations, and possible paths. It is geometry becoming physics. The common rubber sheet image can help for a moment, but only for a moment. A heavy ball placed on a stretched sheet makes a dip, and a smaller ball rolls around it. This gives a rough visual sense that mass changes geometry. But it also misleads because the ball on the sheet is pulled downward by gravity in the first place, and real space-time is not a fabric sagging into an ordinary space below it. The true idea is stranger mass and energy shape space-time from within. There is no need for an outside stage. Space-time is the stage, and the stage is dynamic. This is why the idea is so difficult to domesticate. In Newton's world, gravity happens inside space. In Einstein's world, gravity is tied to the shape of space-time. The container is no longer passive. The geometry of the universe participates in the motion of things. The consequences are subtle at first. A clock near Earth ticks slightly differently from one higher above it. Light passing near the sun follows a path that appears bent. Mercury's orbit carries a small shift that Newton's theory could not fully explain. These are not wild science fiction effects. They are small deviations, tiny fractures in the old picture. But small fractures can reveal deep structure. The great revolutions in science often begin not with total failure, but with a discrepancy too persistent to ignore. Newton's gravity was not wrong in the simple sense. It remains an extraordinary approximation across ordinary conditions. But Einstein showed that beneath Newton's success lay a deeper geometry. Minkowski's unification of space and time made that deeper geometry imaginable. Once space and time became one, gravity could be reinterpreted as the curvature of that unity. A falling apple, the moon's orbit, a ray of starlight passing the sun, and the tick of a clock near Earth all became different expressions of the same invisible structure. But Einstein still needed a bridge from idea to full theory. That bridge began with one of the simplest and most powerful thought experiments in physics, a person inside a falling elevator. It is a scene with no telescope, no star, no black hole, no equation visible to the eye. Just a small, enclosed cabin, falling freely, and a person inside who suddenly feels weightless. From that falling room, Einstein would climb toward curved spacetime. Picture a closed elevator drifting in darkness. There are no windows. The person inside cannot see Earth stars or any outside reference. If the elevator is far from all planets and engines push it upward with steady acceleration, the person inside feels pressed to the floor. A dropped object falls. A body has weight. To the person in the cabin, it may feel exactly like standing in a gravitational field. Now imagine the elevator falling freely near Earth. The cable has snapped in a thought experiment, not in a tragedy, and the cabin drops along with everything inside it. The person floats. A dropped object does not fall to the floor because the floor is falling too. For a moment, gravity seems to vanish. Inside the closed cabin, free fall feels like weightlessness. Einstein called this kind of realization one of the happiest thoughts of his life. The insight was not that gravity disappears in a simple sense. Earth is still there. The elevator is still falling because of Earth's gravity. But locally inside the falling cabin, the person no longer feels the gravitational force. Their body and the objects around them are all following the same natural path. This suggested a profound equivalence. Acceleration and gravity are deeply related. A person in an accelerating rocket can feel something like gravity. A person falling freely in gravity can feel weightless. From this simple contrast, Einstein began to see that gravity might not be an ordinary force at all. It might be connected to the geometry of spacetime and the paths objects follow within it. This is where the mystery changes character. Special relativity had shown that time and space depend on motion. Minkowski had shown that they belong together as space-time. But general relativity asks something even deeper. What if space-time is not flat? What if matter and energy tell it how to curve? What if bodies fall because they are following the straightest possible paths in a curved universe? This idea can sound almost too elegant. But for Einstein, it was not a poetic guess. It was a difficult mathematical and conceptual struggle that took years. He needed a theory that would preserve the insights of special relativity while explaining gravity. He needed equations in which geometry and matter were not separate topics, but parts of one structure. The result was general relativity. In this theory, gravity is not merely a pull between masses. It is the manifestation of curved space-time. Massive objects such as planets and stars alter the geometry around them. Other objects then move along paths shaped by that geometry. A planet orbiting the sun is not being pulled across empty space in the old simple sense. It is traveling along a natural path through curved space-time. This does not make the motion less real. It makes the reality stranger. Imagine trying to walk straight across a landscape you cannot see from above. If the ground curves gently, your path may change, even though each step feels forward. In general, relativity objects moving freely through space-time follow geodesics, the closest equivalent of straight paths in a curved structure. What we call gravity is what that curvature feels like from within. This is why astronauts in orbit are weightless. They are not beyond Earth's gravity. Earth's gravity still shapes their path. They are falling around Earth, continuously moving forward fast enough that the ground curves away beneath them. Their weightlessness comes from freefall, not from the absence of gravity. The same idea, in a simpler form, lives inside Einstein's elevator. Gravity changes from a force you feel to a geometry you follow, but we do feel weight when we stand on Earth. That feeling comes from the ground pushing upward, preventing us from following our natural freefall path. The floor interrupts the geodesic. The pressure in your feet is not simply gravity pulling you down in the old sense. It is Earth stopping you from falling freely through curved space-time. This inversion is quiet but enormous. What feels most like gravity, the weight pressing you to the floor, is partly the result of not following gravity's natural path. Free fall, which feels like the absence of gravity, is in Einstein's theory the state closest to moving naturally under gravity. The world has turned inside out. This reversal is easier to miss than to state. When you stand on the ground, you feel the weight of your body and imagine gravity as the downward thing. When you fall freely, you feel weightless and imagine gravity has somehow disappeared. Einstein asks us to consider the opposite. Standing still on Earth is not the most natural state. Free fall is closer to the natural path. The ground is what prevents you from following it. The floor is always accelerating you away from free fall. This is a strange sentence, but it is central. You feel weight because the ground pushes upward on you. It keeps your world line from following the geodesic it would otherwise take through curved space-time. In everyday language, gravity pulls you down. In Einstein's deeper language, the Earth blocks your natural fall, and the pressure of that blockage is what you feel as weight. This does not make the old language useless. It is still perfectly sensible to say gravity pulls things downward in ordinary life. Physics often keeps multiple layers of description. One layer helps us live and build. Another reveals the structure beneath the approximation. The danger is not in using the everyday phrase. The danger is in forgetting that the phrase is not the final picture. General relativity asks for a new humility about familiar sensations. The feeling of weight is one of the most basic facts of embodiment. It is there when we wake, walk, sit, carry, climb, or lie down. It seems too immediate to be reinterpreted. Yet Einstein shows that even this feeling is not simple. It is a local experience produced by a body prevented from falling freely through a curved space-time. The same reinterpretation applies to orbit. The moon is often described as being pulled by Earth, and that description works well enough in Newtonian language. But in general relativity, the moon follows a geodesic through the curved space-time shaped by Earth and the wider gravitational environment. It is not trying to fly straight in a fixed Euclidean space, while a force yanks it sideways in the old visual sense. The straightest available path is already shaped by curvature. This is why geometry becomes destiny. A planet does not need to know the sun is there. A ray of light does not need to choose a bent path. Each follows the structure available to it. Matter and energy shape space-time, and space-time shapes motion. The two are not separate chapters of reality. They answer one another continuously. There is a quiet grandeur in this. The falling apple, the tides, Mercury's orbit, the light from distant stars, the drift of clocks, and the motion of satellites all become expressions of the same principle. The universe is not held together by invisible ropes stretched across an empty stage. It is organized by geometry, by the way space-time tells possible paths how to unfold. And yet this geometry is not visible in the ordinary way. You cannot look at the air above a road and see space-time curve. You cannot watch time slow around your feet. You cannot see the geodesic of a falling stone. The theory asks us to trust a form of reality revealed by measurement mathematics and repeated prediction, not by raw sensation. This gives general relativity a special kind of beauty. It is both deeply physical and almost ghostly. It explains the things we feel most directly. falling weight orbit in time by appealing to something we do not directly see. The visible world becomes the surface expression of an invisible geometry. And once that geometry is accepted, the sun becomes more than a source of light. It becomes a test of reality's shape. General relativity also changes time again. Gravity affects the rate at which clocks tick. A clock closer to a massive body runs more slowly than one farther away relative to that distant clock. This is not because the clock is damaged or poorly made. It is because time itself is shaped by gravitational potential. Near Earth, the effect is tiny. Near a compact, massive object, it can become much stronger. Near a black hole, it grows into one of the most haunting consequences of relativity. But even here on Earth, the principle is real enough to measure. Atomic clocks can reveal differences in time at different heights. Satellites must account for it. The invisible curvature of space-time has practical consequences. A taller building is not just higher in space. It is slightly different in time. The difference is minute, almost absurdly small for human life. But the meaning is enormous. The top floor and the ground floor do not occupy identical gravitational time. The universe is not dramatic about this. It does not announce the difference with thunder. It lets precision instruments whisper it. Einstein's theory was not merely an interpretation. It made predictions. One concerned Mercury. The planet Mercury closest to the Sun has an orbit whose point of closest approach shifts gradually over time. Newtonian gravity explained most of this motion, especially when the influence of other planets was included. But a small remaining discrepancy persisted. It was tiny, but stubborn. General relativity accounted for it. In Einstein's theory, Mercury moves through space-time, curved strongly by the Sun. The small extra precession of its orbit was not an embarrassment to celestial mechanics anymore. It became a sign that the geometry near the Sun was slightly different from Newton's expectation. There is something almost poetic about the smallness of this clue. The revolution did not begin with the planet flying wildly off course. Mercury did not rebel against the heavens. It simply shifted a little more than expected year after year, quietly refusing to fit the old calculation perfectly. The universe often reveals deeper truth through such small refusals. A tiny excess in an orbit can carry the weight of a new cosmos. This was a powerful internal victory, but it was not enough for the world. The public drama would come from light. If the Sun curves space-time, then not only planets should be affected. Light passing near the Sun should follow a curved path as well. In Newtonian thinking, light had sometimes been imagined as particles that might be influenced by gravity, but Einstein's prediction had a distinct relativistic form. The Sun should bend starlight by a measurable amount. The problem was simple to state and difficult to test. Stars near the Sun are usually hidden by the Sun's brightness. To see them, astronomers needed a total solar eclipse when the Moon briefly covers the Sun and the surrounding stars become visible in daytime darkness. If photographs taken during the eclipse showed those stars shifted from their usual positions, the bending of light could be measured. This turned space-time into an observational quest. Suddenly, the geometry of the universe could be tested not only through equations, but through a darkened sky. A theory born from clock's light, beams falling elevators, and mathematical struggle would face the Sun itself. The question was almost impossibly delicate. Would starlight passing near the Sun carry the fingerprint of curved space-time? Before that answer, the idea remained strange. Gravity as geometry asked people to surrender a deeply familiar picture. It asked them to stop imagining space as merely the container of events. It asked them to imagine the container as dynamic. It asked them to see falling, orbiting, bending light and ticking clocks as part of one structure. The falling elevator had opened the path. Inside that imagined cabin, gravity lost its ordinary form. The person floating inside did not feel pulled. They were following a path. From that small interior scene, Einstein reached outward to the sun, to Mercury, to the motion of light, and eventually to black holes and waves moving through space-time itself. The scale changed, but the mystery remained one. What we feel as gravity may be the shape of the invisible. And if that is true, then the next test would not simply decide whether Einstein had made a clever theory. It would decide whether the sky itself agreed that space and time could bend. The next section takes that idea into the sky, where a solar eclipse made Einstein famous, where light revealed the curvature around the sun, and where the same theory would later lead to the darkest objects in the universe. In 1919, the proof of Einstein's strange idea depended on a brief darkness. A total solar eclipse would cover the sun turning day into a temporary night, and allowing astronomers to photograph stars close to the sun's apparent position. Those stars were not physically near the sun. They were far behind it. But their light passing through the curved space-time around the sun should appear slightly shifted. The measurement was tiny. The conditions were uncertain. Clouds could interfere. Photographic plates could be difficult. The world had just come through the First World War. Science, politics, exhaustion, and hope all surrounded the expedition. Arthur Eddington, Frank Dyson, Charles Davidson, and others became part of an event that was both technical and symbolic. The question was simple in words: does the sun bend starlight? But behind that question stood an entire picture of reality. If light followed a curved path near the sun in exactly the way Einstein predicted, then gravity was not only a force acting on mass, it was a change in the geometry through which even light must travel. When the results were announced, Einstein became a global figure. Newspapers transformed him into a symbol of genius almost overnight. The public story became simple. Newton, overthrown; Einstein, triumphant. The universe changed by an eclipse. The real history was more careful and more complicated, but the symbolic power was undeniable. A darkened sun had helped reveal that space and time were not rigid. Starlight had become evidence of curved space-time. This is one of the great images in the history of science: light, from distant stars traveling across space for years, grazing the sun, bending by an amount too small for ordinary eyes, then arriving on a photographic plate where human beings tried to measure a new geometry of the universe. The universe did not shout its answer. It shifted a star's apparent position. That shift opened a door. If the sun can bend light, then more massive and compact objects can bend it more dramatically. Entire galaxies can act as gravitational lenses, warping and magnifying the light of objects behind them. Space itself becomes an optical instrument not made of glass, but of gravity. The path of light becomes a map of invisible mass and curved geometry. This gives the universe a strange kind of transparency. Mass can reveal itself by how it distorts what lies behind it. A galaxy cluster can bend the light of distant galaxies into arcs. Invisible dark matter can be inferred by the gravitational lensing pattern it leaves on passing light. The geometry between us and a distant object becomes part of the image itself. Looking into space is no longer only looking at things. It is also looking through curved space-time. The deeper we go, the stranger the geometry becomes. One of the first exact solutions to Einstein's field equations was found by Karl Schwarzschild during the First World War. His solution described the space-time outside a spherical, non-rotating mass. At first, it was a mathematical result, elegant and unsettling. Hidden in it was a radius that later became central to the idea of black holes. If enough mass is compressed inside a small enough region, space-time can form an event horizon. An event horizon is not a solid surface. It is not a wall floating in space. It is a boundary in causality. Beyond it, the paths that light and matter can take no longer lead outward. The future, in a sense, tilts inward. Once inside every possible direction through space-time carries the object deeper. This is why black holes are so much more than heavy objects. They are places where space-time closes. The phrase, "nothing can escape," is true, but it can sound too simple. The deeper idea is that escape routes themselves have disappeared. It is not that a rocket merely needs more power and fails. It is that the structure of possible futures has changed. Beyond the event horizon outward is no longer a future-directed path back to the outside universe. This is one of the most haunting consequences of general relativity. Einstein himself was cautious about some extreme implications of his theory, and black holes took time to become accepted as physical realities rather than mathematical oddities. The path from Schwarzschild's solution to modern black hole astrophysics was long. It passed through stellar collapse, neutron stars, singularity theorems, X-ray, astronomy, galactic centers, and eventually direct imaging of black hole shadows. A massive star can spend millions of years balancing itself. Gravity pulls inward. Nuclear fusion pushes outward. The star shines because it is fighting collapse from within, turning light elements into heavier ones and releasing energy in the process. But when the fuel runs out, that balance can fail. For the most massive stars, the core can collapse under its own gravity, compressing matter into states beyond ordinary imagination. If the collapse goes far enough, no known pressure can halt it outside the formation of a black hole. This is not simply an object becoming dark. It is space-time changing its causal structure. A region forms where all future-directed paths lead inward. The star has not merely become hard to see. It has created a boundary beyond which seeing outward is no longer part of the future. Roger Penrose's work helped show that black holes were not merely artifacts of perfect symmetry. Under broad conditions, gravitational collapse could lead to trapped surfaces and singularity formation within general relativity. This made black holes harder to dismiss as mathematical curiosities. They became a robust prediction of the theory. But the word singularity carries danger. In the mathematics of general relativity, singularities indicate places where quantities can become infinite or where the theory no longer describes space-time in the usual way. Many physicists do not treat this as a comfortable physical object, like a tiny bead of infinite density sitting at the center. Instead, it is often understood as a sign that the theory is being pushed beyond its domain toward a place where quantum gravity may be needed. The event horizon can be described by general relativity. The deep interior asks harder questions. This makes black holes perfect for the story of space-time. They are not just exotic objects. They are limits made visible. They show what happens when space-time curvature becomes so extreme that ordinary intuition fails completely. Near them, time and light behave in ways that feel almost mythic, yet arise from precise equations. To a distant observer, matter falling toward a black hole appears to slow and redden near the horizon. Its light stretches to longer wavelengths. Its clock, as seen from far away, seems to fade into delay. For the falling object itself, the experience is different. Relativity refuses to give one single universal account because time belongs to paths through space-time. The old master clock is gone. Black holes are not only theoretical. Astronomers have found strong evidence for stellar mass black holes and supermassive black holes. At the center of our own Milky Way lies Sagittarius, a star, a compact massive object whose surrounding stars move in ways that reveal an enormous hidden mass. In 2019, the Event Horizon Telescope released the first image of a black hole shadow in the galaxy M87, and later an image of Sagittarius, a star. These images did not show the event horizon directly like a surface. They showed glowing material around a dark central shadow shaped by extreme gravity. Still, their emotional power was enormous. Something predicted from equations had become an image blurred but real. A dark absence ringed by light. There is a strange calm in those images. They do not look like explosions. They do not show a monster with teeth. They show a shadow where light cannot return, surrounded by matter, heated to extraordinary energies. They show not only an object, but a geometry. The darkness is meaningful because space-time has arranged the paths of light in such a way that part of the universe is hidden from us. A black hole is an absence with structure. The closer we imagine approaching a black hole, the more ordinary language begins to fail. From far away, it may be tempting to picture a black hole as a dark sphere in space, a kind of cosmic object with an edge. But the event horizon is not a material skin. There is no solid surface waiting there, no crust, no wall, no place where an astronaut would necessarily feel a sudden physical impact simply because the horizon had been crossed, especially for a sufficiently large black hole where tidal forces at the horizon could be mild. The horror is subtler. The event horizon is a boundary in what can be communicated to the outside universe. It is a change in causal possibility. Outside it, a flash of light can still travel outward if aimed properly. Inside it all, future-directed light paths lead deeper inward. The horizon does not need to stop light like a wall. It changes what outward can mean. This is why black holes are so important for spacetime. They show that geometry can become destiny in the most extreme sense. Not destiny as fate or myth, but as the structure of possible paths. Once inside, the future is not open in all the ways it seemed outside. The geometry of space-time has narrowed the available directions until every route leads inward. A black hole, therefore, is not only an object with strong gravity, it is a region where the future has a shape. That phrase is strange, but it belongs to Einstein's universe. In everyday life, the future feels open in many directions. You can turn left, right, climb, descend, wait, return. Near and inside a black hole, the geometry governing such possibilities changes. The paths that remain allowed are not organized like the paths around Earth. This is also why time near black holes fascinates us so deeply. A distant observer watching something approach the horizon sees its signals slow, redden, and fade. The falling object itself does not experience its own clock stopping at the horizon. Its local time continues along its own path. Again, there is no single master story of time that everyone shares. There are relations between observers, signals, and world lines. The black hole makes this impossible to ignore. It takes the quiet fact of satellite clocks and magnifies it into cosmic drama. Time is not uniform. Paths matter. Gravity matters. Signals matter. The universe does not contain one simple now. Around a black hole, that truth becomes almost cinematic, as if the geometry itself were teaching us the lesson in darkness. But even here, caution matters. Popular imagination often turns black holes into absolute monsters, cosmic vacuum cleaners devouring everything nearby. Real black holes do not pull distant objects more strongly than any other object of the same mass would from far away. If the sun could somehow be replaced by a black hole of the same mass, Earth would not be instantly sucked in. The danger lies in extreme closeness, in compactness, in crossing regions where space-time curvature becomes severe. The black hole is frightening not because it is magical. It is frightening because general relativity is being taken seriously. That seriousness is what makes the later detection of gravitational waves so powerful. Black holes were not merely dark speculations. They could orbit one another, spiral inward, merge, and disturb space-time itself. A horizon could collide with another horizon. The geometry could settle into a new form. The violence of the event could leave Earth with only a tiny whisper, and that whisper was enough. And then space-time did something even stranger. It rang. Einstein's theory predicted gravitational waves, ripples in space-time, produced by accelerating masses, especially violent cosmic events such as merging black holes or neutron stars. For decades, these waves remained extraordinarily difficult to detect. The effect by the time such waves reached Earth would be almost unimaginably small, a stretching and squeezing of distance, far smaller than anything ordinary instruments could notice. Yet scientists built instruments to listen. LIGO, the Laser Interferometer. Gravitational Wave Observatory used long arms and laser light to measure tiny changes in length. A passing gravitational wave would stretch one arm and compress another by an almost impossibly small amount, then reverse the pattern. The challenge was not only detecting the signal, it was separating it from vibrations, noise, thermal motion, seismic disturbance, and countless earthly interruptions. The detectors had to be almost impossibly patient. They waded through noise. They waded through calibrations. They waited while trucks moved. Wind past the ground, trembled. Mirrors quivered, and human engineering tried to isolate a signal smaller than imagination wanted to accept. The instrument was listening not for sound in air, but for a change in distance caused by a ripple in space-time itself. For years, the universe was quiet. Then, on September 14, 2015, a signal arrived. It came from two black holes merging more than 1 billion years ago. As they spiraled together, they lost energy in gravitational waves. Their orbit tightened. The frequency rose. In the detectors, the signal appeared as a brief chirp, a rising tone translated from space-time into human hearing. The fabric had rippled, and Earth had listened. This was not a metaphor in the loose sense. The distances inside the detectors had changed because space-time itself was being stretched and squeezed. By the time the wave arrived, the effect was tiny, but it carried news of an event unimaginably violent and distant. Two black holes had merged, and the disturbance crossed the universe at light speed. For a fraction of a second, the merger released a staggering amount of energy in gravitational waves. But by the time that ancient disturbance reached Earth, it was gentle beyond sensation. It passed through the planet, through oceans, mountains, cities, and sleeping bodies, unnoticed by everything except instruments built with extraordinary care. The universe had spoken in a language our senses were never designed to hear. The discovery opened gravitational wave astronomy. For the first time, humanity was not only seeing the universe through light, it was sensing space-time's own vibrations. Black holes, neutron stars, and extreme collisions could be studied through a new messenger. The invisible fabric had become an instrument of cosmic communication. This is the great arc of Section 5. First, the sun bends starlight. Then black holes close space-time around themselves. Then merging black holes send ripples through the dark. A theory that began with clocks and thought experiments becomes a way to understand the most extreme events in the cosmos. Space-time is no longer passive. It bends, it traps, it shakes, it carries waves. Yet the more real space-time becomes, the deeper the mystery grows. If space-time can behave like this, what is it? Is it a thing? Is it geometry? Is it a field? Is it fundamental? Or does it emerge from something deeper? General relativity gives stunning answers, but it also points toward places where its own language begins to strain. The sun showed that space-time curves. Black holes showed that space-time can close. LIGO showed that space-time can ripple. And now the final question waits beneath all of them. If space-time is the fabric of reality, What is the fabric made of? Einstein's theory made spacetime more real than it had ever been. It was no longer a philosophical background or a mathematical convenience. It could slow clocks. It could bend light. It could shape orbits. It could form horizons around black holes and ripple across the universe after cosmic collisions. Again and again, observation confirmed that the invisible geometry was not optional. It was part of how reality works. And yet the mystery did not end. In fact, general relativity opened new questions so large that physics is still living inside them. One of the first came from the universe itself. Einstein's equations did not describe only planets and stars. They could be applied to the cosmos as a whole. This meant spacetime was not only local, not only curved around objects, not only distorted near mass. The entire universe could have a spacetime history. At first, many scientists, including Einstein, expected the universe to be static on the largest scale. A static universe felt natural. Stars moved planets, orbited galaxies existed, but the whole cosmic structure was often imagined as broadly unchanging. Einstein even introduced a cosmological constant into his equations to allow for a static universe. Later, the expansion of the universe would change the meaning of that term in ways that still echo through cosmology. Alexander Friedmann found dynamic solutions to Einstein's equations. Georges Lemaitre connected the mathematics to an expanding universe. Observations of galaxies and their redshifts helped reveal that the universe is not static. Space itself on cosmic scales is expanding. This is another blow to common sense. Galaxies are not simply flying through a pre-existing emptiness, like fragments from an explosion moving into a room. The distances between faraway galaxies grow because the scale of space itself changes. Light, traveling through this expanding universe, stretches with it becoming redder as its wavelength lengthens. Space-time is not merely the arena of cosmic history. It has a history. This idea can be hard to hold because our imagination wants expansion to happen into something. We picture a cloud growing in air, a balloon swelling in a room, an explosion spreading outward into empty space. But cosmic expansion is stranger. It is not simply matter moving through space. It is the scale of space between distant galaxies changing with time. The universe is not expanding into a known outside. The outside is not part of the description in the simple way imagination demands. General relativity allows space-time itself to be dynamic. The distance between distant regions can grow because the metric, the way distance is measured across space-time, changes. This is a deep extension of the same revolution. The background is not fixed. The background evolves. This leads backward toward the Big Bang, not as an explosion in space, but as an early hot dense state of the universe when the scale factor was far smaller and conditions were extreme. The farther back cosmology looks, the more space-time itself becomes part of the question. What does it mean for the universe to have an age? What does it mean to ask what happened before time, if time, as we know it, belongs to the universe's space-time structure? Such questions are delicate. Physics can describe much about the early universe, but the very beginning pushes theory toward limits. General relativity, followed backward under simple conditions, points toward a singularity, a place where density and curvature seem to become infinite, and the known equations lose their ordinary meaning. But many physicists take this not as a final description of reality, but as a warning. A singularity may be a signpost saying this theory has reached the edge of itself. The same warning appears inside black holes. General relativity describes the formation of horizons and the structure outside them with extraordinary power. But deep inside, where curvature becomes extreme, the theory points toward a singularity. If quantum effects become important there, then classical spacetime may no longer be enough. The smooth geometry of Einstein may need to be replaced or completed by something deeper. This is the unresolved meeting place of general relativity and quantum mechanics. General relativity is the great theory of the large, the massive, the geometric. It describes planets, stars, galaxies, black holes, and the expansion of the universe. Quantum mechanics is the great theory of the small, the probabilistic, the discrete, and the uncertain. It describes atoms, particles, fields, radiation, and the structure of matter. Both are astonishingly successful. But when gravity must be understood at quantum scales, the harmony breaks. Near the Big Bang, inside black holes, and perhaps at the smallest scales of length and time, we need a theory that understands both quantum behavior and space-time geometry. This is the problem of quantum gravity. It is not merely a technical gap. It asks whether space-time itself is fundamental. That question is almost too deep to hold. In general, relativity space-time is smooth. It can curve continuously. It forms the structure in which events occur. But quantum physics often reveals that quantities once thought smooth may have discrete or uncertain aspects. If space-time has a quantum nature, then perhaps the smooth fabric we experience is not the final layer. Perhaps space-time is emergent. To say space-time may be emergent is not to say it is unreal. A wave on the ocean is real, even though it is made from the collective motion of water. Temperature is real, even though it emerges from the motion of countless particles. A melody is real, even though it depends on vibrations, timing, and pattern. Something can be emergent and still shape experience powerfully. Space-time, if emergent, would be real in that deep practical sense. It would still guide a planet's slow clocks, bend light, and carry gravitational waves. General relativity would still work where it works. But space-time might not be the final vocabulary of nature. It might be a large-scale description, smooth and beautiful, arising from a deeper level that does not itself look like space or time. This possibility is difficult because all human imagination begins inside space-time. When we try to imagine something deeper, we almost automatically place it somewhere. We picture tiny threads, grains, loops, networks, or surfaces. We ask when it began, where it exists, what it is made of. But if space-time itself is what gives meaning to where and when, then the deeper level may resist ordinary spatial and temporal pictures. The mind keeps trying to build a room outside the room. That may be impossible. This is one reason quantum gravity is so hard to turn into simple narration. It is not only another unknown particle or another distant astronomical object. It challenges the language in which objects and distances are described. It asks what physics means when the stage itself is no longer assumed. Some approaches suggest that space-time might have a granular structure at extremely small scales. Others explore whether gravity and space-time are connected to information entanglement or holographic relationships. Others try to preserve geometry while quantizing aspects of it. These ideas are subtle, unfinished, and mathematically demanding. The important point for this story is not to choose a winner. The important point is that Einstein's mystery remains alive. General relativity made space-time dynamic. Quantum gravity may require space-time to become something even stranger, not only flexible, but perhaps derived. not only curved, but perhaps composed from relationships that are not spatial in the ordinary sense. Not only the fabric of reality, but a fabric whose loom is hidden. This gives the ending of the story a different feeling. We do not leave Einstein behind as a solved chapter. We stand inside the universe he revealed, using his theory every time we correct satellite clocks, study black holes, or listen for gravitational waves. But we also stand at the edge of questions his theory helped create. The better general relativity works, the more seriously we must take the places where it reaches its limits. That is not a failure of Einstein. It is the mark of a great theory. A great theory does not merely answer old questions. It creates sharper questions than the ones that came before. Newton made gravity universal. Einstein made gravity geometric. The next theory, if it comes, may ask what geometry itself is made from, and perhaps that is the deepest reason spacetime remains so moving. It is familiar enough to contain every ordinary life, every room, every road, every sunrise. It is precise enough to guide satellites and predict the motion of planets. It is vast enough to describe the expansion of the universe. It is extreme enough to form black holes and carry ripples from collisions older than human civilization. Yet it may still not be the final floor. Under the fabric there may be another order. Not a place beneath in the ordinary sense, but a level beneath explanation. A structure from which distance, duration, curvature, and causality arise. We do not yet know how to speak of it clearly. We only know that the questions point there, and so space-time becomes both answer and invitation. This is not a settled answer. It is a frontier. Different approaches imagine the problem differently. Some explore strings loops, holography causal structures, quantum information, or other mathematical frameworks. These ideas are not all equivalent, and none has yet become a fully confirmed final theory of quantum gravity. The uncertainty must remain, but the possibility changes the emotional meaning of Einstein's achievement. Einstein revealed that space and time are not fixed containers. They are dynamic, relational, responsive to matter and energy. Yet by making space-time so central, he also made its mystery sharper. If gravity is geometry, then what is geometry made of when the universe is viewed quantum mechanically? The fabric may not be woven from threads we can picture. It may be woven from relations information fields, symmetries, or something for which ordinary language is still too clumsy. The deepest level may not resemble a fabric at all. Fabric is only a human image, useful for a while, then limited. This is why the documentary cannot end with Einstein simply solving gravity. He did solve something enormous. He showed that gravity could be understood as curved space-time. He explained Mercury's orbit, predicted the bending of starlight, revealed gravitational time dilation, and opened the path to black holes, cosmology, and gravitational waves. His theory remains one of the most beautiful and successful structures in science. But the success does not close the mystery. It deepens it. The universe Einstein gave us is more precise than Newton's in extreme conditions, but also less familiar. There is no universal now. Time bends with motion and gravity. Space can expand. Light follows the curvature around mass. Black holes hide regions from which no path returns. Space-time itself can tremble. And at the boundaries where the equations point towards singularities, science encounters silence. Not empty silence, but the silence of unfinished knowledge. The kind that asks for new mathematics, new experiments, new patience, and perhaps new intuition. The question is no longer only how objects move through space-time. It is whether space-time is the final stage on which physics happens, or whether physics must one day explain the stage itself. This brings us back to the clock. A clock above Earth ticks differently from one below. A clock near a massive object would differ more. A clock near the edge of a black hole would become part of an almost unbearable distortion in the eyes of a distant observer. Time, which once seemed the simplest background, becomes a local measure of a path through space-time. That path is real, but perhaps it is not ultimate. If space-time emerges from deeper principles, then every clock, every orbit, every beam of light, every gravitational wave may be a surface expression of something more hidden. Not hidden in the sense of mystical secrecy, but hidden in the scientific sense, not yet understood, not yet measured directly, not yet translated into a stable theory. Einstein's greatest mystery is not only that space and time are strange, it is that their strangeness may still be incomplete. We began with ordinary intuition. A clock ticks, space holds gravity, pulls. Then the clock betrayed common sense. Light refused to be chased. Space and time became one. Gravity turned into curvature. The sun bent starlight. Black holes closed the paths of escape. The dark universe rippled with waves from colliding horizons. Each step made space-time more visible. Each step also made it harder to say what space-time finally is. Perhaps that is the quiet beauty of the story. Science does not always make the universe smaller by explaining it. Sometimes it makes the universe larger, deeper, and more mysterious, even as it becomes more precise. Einstein did not remove wonder from gravity. He gave gravity a new depth. He taught us that the ground beneath our feet is not merely beneath us. It is part of a curved geometry. The time in our bodies is not simply universal. It is local, fragile, and woven into motion. The night sky is not a flat backdrop. It is a space-time history filled with signals, horizons, waves, and distance stretched by cosmic expansion. And beneath all of it, the fabric remains, not silent, not simple, not fully understood, only waiting for the next question. By the end of this journey, space-time no longer feels like an empty stage. It feels closer, stranger, and more alive than ordinary intuition allows. It is there in the quiet correction of a satellite clock, in the path of a beam of light, in the invisible curve around the sun, in the boundary of a black hole, and in the faint gravitational waves that pass through Earth after traveling across cosmic darkness for more than 1 billion years. Einstein did not simply give science a better theory of gravity. He changed the shape of the question. Gravity became geometry. Time became flexible. Space became dynamic. The universe became something whose structure could respond to matter, energy, motion, and light. And still the mystery remains open. At the edges of black holes near the beginning of the universe, and deep inside the unresolved meeting place of general relativity and quantum mechanics, spacetime begins to look less like the final answer and more like a surface hiding something deeper. The fabric explains so much, yet it also points beyond itself. Perhaps that is why spacetime remains one of Einstein's greatest mysteries. It gave us a universe more precise than before, but also more mysterious. It showed us that reality is not built from the simple background our senses imagine. It is woven from relationships, motion, curvature, limits, and questions still waiting in the dark. And somewhere above us, another satellite clock is ticking quietly, reminding us that even time itself is not as simple as it seems.